are you?
I have a couple of questions I will make you later when you allow me to do it. All
right, sounds good.
Can you hear me? Can you hear me?
Yeah, but a bit low, but I can.
Okay, great. Yeah, later.
No sé si se perdió, pero
I share the screen again. We have 1 minute still, but just to get prepared.
Yeah, go on, yeah.
Can you see it?
Yeah.
Okay. So let me know when I should restart, okay?
Okay.
No, tenemos que coger un con el teléfono porque no primero, sino primero solo.
No, es aquell ordinador, és l'ordinador. Yeah. So, do you want us to make you the questions now or later, or?
Well, it's up to you.
Okay. So my question is, how do you compute the Lyapunov exponents when you have dynamical parameter? I mean, can you use the same technique? For instance,
Yes,
okay.
You have two ways to do it. You can simply have a Jacobian matrix where one of the parameters is time dependent.
You
have the 9 Lyapunov exponents with them either negative, 0, or positive. Or, and we have done this, I might send you a reference, or we can simply make an autonomous system where we include a hope verification, a hope oscillator, I'm sorry, which gives you a 2x equation, and one of the 2x Lyapunov exponents, and one of this Lyapunov exponent would be 0, the other one would be the contraction.
Yeah.
They give the same result.
Okay, thank you.
Yeah.
Now Tomás is going to make a couple of questions. Okay, hi Maíra. Very nice talk.
Shall I stop sharing so we can see each other, or?
I think you can. Okay, I'm going to in front of the TV, of the camera.
Okay, so I can see.
Can you see me? Okay, yeah. First question: assume that you have a way to compute numerically a particular value of beta in a certain moment. You could, for instance, instead of dealing with a periodic force of infection beta, you could just substitute by a piecewise continuous function, keeping the value of beta fixed for, say, the period. Do you expect to have similar results that the ones you have get now? Because in particular, you can compute the Lyapunov exponents because now the system is autonomous and it's easier to do it. Do you expect to have some similar things?
No, I think that, overall you would get the same thing, but then because of this piecewise, you would get these jumps. So it would not be as nice as the way we are doing.
Okay.
And notice that the system, let me share again, and then you can see it. I can come back if you have more questions. This is the behavior for the non-seasonal model. Without seasonality, by only adding the structure of strains, we get this complicated behavior, this complicated dynamics. And in our case, a nicer and more realistic one for assuming the contribution of secondary infection smaller than the contribution to primary infection in the population. And when we add seasonality, this one here becomes completely cloudy. So it puts chaotic all over.
Okay.
Yeah.
Okay, thank you. And my second question is, okay, you're assuming that you're having two strains of dengue viruses.
Yes.
And you're assuming that they follow, in the seasonal case, they follow the same period. Assume, for instance, that you don't have exactly the same period. So instead of dealing with a periodic function, you have a quasi-periodic function. Is it going to complicate much the model? And do you think it will be similar to the case or more accurate what happens in reality?
No, I mean, for the moment, we do not consider asymmetry between the strains. I assume that they are coexisting and the individuals can get infected with one or another. And after recovering from this primary infection, that could be any time, this individual becomes susceptible by assuming this temporal cross immunity of being at least 6 months. So at this moment, I do not have any issue on asymmetric modeling. When we add asymmetry, we have looked at it, but not really deep. We still get the complicated dynamics. But the asymmetry has to be really small because if it is big, one of these strains would get extinct.
Okay. So thank you very much, Maíra. Thank you.
Yeah. You are welcome. So I will share again so we can continue. Yes. Thank you for the questions, and I'm here if you want to ask anything else. Just to let you know that by only adding the strain structure to the system, we get already chaotic dynamics going on, and I will show you that it is for sure. This new chaotic window here, it's new and is really interesting for us, especially me coming from the laboratory where we observe this kind of behavior in reality. So we kept for the past 15 years analyzing this parameter region here for dengue. So here the computation of the Lyapunov exponent. Again, the definitions when we have negative, when all the Lyapunov exponents are negative, we have fixed point. When one of the Lyapunov exponents reach 0, you have a limit cycle, so a periodic behavior. And when the Lyapunov exponent is positive, it means that it's chaotic. We kept analyzing the parameter phi, so the ADE ratio between 0 and 1, that it didn't exist in the 1999, but by adding temporal cross immunity, we find it. And we saw that this parameter region here is so rich in terms of dynamic that has shown via the bifurcation analysis, not only hope bifurcation, but also pitchfork, torus, and tangent bifurcation, including the deterministic chaos, which was checked or validated by the Lyapunov exponent calculation. So we have a positive Lyapunov exponent for the parameter 5 between 0.5 and 1. So in terms of state space, again, this is a non-seasonal model. We have variable phi values. So assuming that individuals in the primary infection transmit much more than individuals in the secondary infection, we have fixed point, we have limit cycle, and we have the chaotic dynamics for phi equals 0.6 that get stabilized for phi equals 0.1, complicated limit cycle, and the previously described chaotic behavior for Ferguson, assuming that the individuals in the secondary infection would then transmit 3 times more than individuals in the primary infection. So it's a super rich system, even though there is no external force into it. In terms of time series, we see that we have outbreaks every 4 to 5 years, and it's not data-like, but we know all that dengue is a seasonal disease. And as soon as we add seasonality, we get a realistic pattern with yearly outbreaks that can be compared to the data we have. So we get qualitative, a very good result when comparing empirical data and the model simulation. And remember yesterday in the class that I mentioned to you the definition of chaotic behavior. We have a short-term predictability and long-term unpredictability. And of course, the Lyapunov exponents are very important to tell us what is the limitation of prediction horizon of our model. And of course, we would never be able to match 30 years of data but bits and bits having a chaotic system. So the main message here is that when you have a model which gives you prediction for the next 30 years, please doubt. That cannot be possible. Okay, so in terms of Lyapunov exponent, we did an exercise, and now it's already using the seasonal model. We have the same Lyapunov exponent that we have calculated for the non-seasonal. Oops, we calculate for the seasonal. And we see here that for phi below 0.2, we have all the Lyapunov exponents being negative, which means we have fixed point. The Lyapunov exponent reaches 0, goes negative again, and then reach 0 with the second. So this is the autonomous system. So we have one Lyapunov exponent here for the limit cycle 0, and we have the second one contracting. And it reaches 0 and gives a so-called torus bifurcation where we have two Lyapunov exponents. This is also characteristic. Has a bit of noise here for the positive and become positive, really positive for phi equals 0.6, around 0.6. So for the parameter region we use to match the data with the model simulation, we assume that individuals in the secondary infection transmit the disease 10% less than individuals in the primary infection. For this parameter set, for this parameter value here, the dominant Lyapunov exponent is equal 0.118, which gives us approximately 9 years of prediction horizon. Okay, so we got this information, and then we are going to test if that's correct. So what we have here, we have an attractor in red, so the first simulation of our model. And then we perturb the system a little bit. So we just start with a very slightly different initial condition, and we run the model and we plot one attractor on top of the other attractor. And we see that, in fact, we have 9 years where both of the trajectories are coinciding, but after that, we no longer can trust the system. So that's the characteristic of chaotic dynamics. You have, in this case, for this system, 9 to 10 years prediction horizon where we have accurate prediction, but after that you need to restart again to rematch the model again to see what else we have as a output in the term of time series. Okay, so we did a lot of research on this system. We have checked the difference by adding 3 strains only or 4 strains only, and here just to illustrate the similarities between a model with strain structure with 2, 3, or 4 strains, because I remember that that was my PhD project actually, and I was challenged by Odo Dickman to look at the 4-strain model because dengue has 4 strains and I should look at it. And so I was challenged and I took the challenge, and in the end there was not much difference. We look at the temporal cross immunity, for instance, the parameter alpha, and we can see that we only have complicated dynamics by assuming temporary cross immunity to be longer than a week, to be longer than first described in 1999. And in terms of attractors, you see that for the same parameter region, both models have the same attractor structure. And we end up with comparing the 2-strain model with the 4-strain model, which is much more complicated. There is a problem in dimension, so we moved from a 10 ODE system to a 26 ODE system. The dynamics are exactly the same. The difference that you can get here infected for the first time with strain 1, 2, 3, or 4. And then the secondary infection, you have more combinations. Instead of two combinations, you have 3 combinations, having seen 1, 2, 3, or 4 strain. Okay. And when we look at it in terms of time series output, the 2-strain model and the 4-strain model looks qualitatively pretty similar, with the data in red and the model output in blue. And when we look at the bifurcation diagram, I have the 2-strain model plotted in green and the 4-strain model plotted in, the 2-strain model plotted in red and the 4-strain model plotted in green. The bifurcation diagrams look pretty much the same. And in quantitative, in terms of Lyapunov exponent, we have the same magnitude for this parameter phi equals 0.9, the same order of magnitude, the same prediction horizon. So the prediction is 9 years, either one model or another. For that given parameter set, we chose to match the data. And of course, we end up with a problem. We need now to analyze control measures. We have other questions to answer. Which model do we use? We use the 4-strain model, we use the 2-strain model. And we like simple things. We use the parsimony law, and we simply took the 2-strain model as being the model able to give us the most information in the simplest version as possible. And this model then was kept used to further extensions and further questions to answer further questions. Okay, so, and remember that till end of 2015, there was no vaccine, but then in 2016, there was a vaccine, and we want to understand what happened with this vaccine. And for the vaccine, we can also model the test, so the trial of a vaccines. And here I comment or I introduce more epidemiological terms, such as vaccine trial, relative risk of a vaccine, and vaccine efficacy. So what is a vaccine trial? Vaccine trial is that you have a product and you need to test this product to see if it is avoiding the individual to become sick or not. So you get a group of people that you follow. To some part of the group, you give the vaccine, and another part, you give something, but it's not a vaccine, what we call placebo. After giving this, you follow this group and count how many disease cases you have in the group receiving the vaccine and how many disease cases you have in the group receiving another product, not vaccine. And by looking at it, you can calculate what is called relative risk. That's the ratio of the number of people having receiving the vaccine and becoming ill, and the group of individuals receiving the placebo and becoming ill. And this relative risk can be one-to-one transfer to vaccine efficacy is simply 1 minus the relative risk, gives you the vaccine efficacy, and that's the value we use. So when the relative risk is larger than 1, which means that you have more people infected in this group receiving vaccine than people in the group not receiving vaccine, we have a negative vaccine efficacy, which means that the vaccine is generating more cases of the disease than in a population without this vaccine. However, when this relative risk is smaller than 1, you have more people having experienced the disease after receiving the placebo rather than the vaccine, than the vaccination group. So we have what's so-called positive vaccine efficacy, which means that the vaccine is protective. When the relative risk is equal 1, there is no vaccine efficacy. So the vaccine is not good or not bad, okay? So for the dengue vaccine, for the Sanofi vaccine, dengue vaccine, the vaccine was given in 3 doses at months 0, 6, and 12. The group size for the vaccine group was twice the size of the placebo group. And after following them for 4 years, they just checked the value of the relative risk. We were able to model this study, and we were able to extract or to have the same results that was published in terms of the vaccine this vaccine efficacy. How did we model vaccine trial? We have 2 groups. We have a control group which receive the placebo, and that means that susceptible in the control group would eventually get in contact with an infected individuals and would become infected with infection rate beta. Again, constant population size here. And the vaccine group, you have the vaccinated individuals eventually encountering these infected individuals and become infected with an infection rate C beta. And what we want is that the C decreases the value of beta. So we expect that the vaccine is helpful, and those vaccinated individuals would become infected at lower level than individuals which didn't receive vaccine, okay? So the vaccine efficacy that we call K can be written explicitly 1 minus this constant C here, which is itself the relative risk. So 1 minus the relative risk, okay? Okay, so this is the table for the vaccine trial of Sanofi Pasteur. I'm not going to enter in detail. So we have 3 groups of the analyzed CYD14, CYD15. So this is Asia, this is South America, and this is Thailand in the phase 2B. We are going to concentrate in the CYD14, where they cover all age groups. So we cover individuals between 2 to 5 years old, 6 to 8, 9 to 11, and 12 to 16. We also analyze this data here, but you see here for the CYD15, which is Latin America, they only look at the older 9 years old of age. And you see that there is a problem with this age group here and why. Okay, so what they say is that the year 1 and 2, we have below 1 relative risk. So we have a positive vaccine efficacy, even though in the confidence interval we have negative vaccine efficacy going on. For all classes 2 to 5, 6 to 8, we also have below 1 relative risk, 9 to 11 below 1 relative risk, and 12 to 16 below 1 relative risk. And as older you grow, better the relative risk, so better the vaccine efficacy is. And we were wondering why. We could compute that, and here there is for the Latin America and for the Asian Pacific. They have published this value of overall vaccine efficacy, and that's what we got from our Bayesian approach. So we just estimate K via the Bayesian analysis, where this gives the median and the confidence interval, and we were really good with what they have published and what we got in terms of data. Okay, good. But when I look at the year 3, we see that the relative risk is much higher than 1. So there was something going on here. That means that those individuals between 2 to 5 years old of age were experiencing more infections than individuals which didn't receive the vaccine. When you look at the other age classes, the relative risk was below 1. Here was just 1, and here was below 1. So there was a problem with these young ages, and we wanted to understand why. While that was under investigation, this vaccine was then not recommended to be given to children under 9, but only to individuals between 9 to 45. Okay? And then we look at the year 4, and we see that still the relative risk for younger than 9, for the younger than 9 was still above 1, but the age class that the vaccine was recommended also had a larger than 1 vaccine efficacy. So there was reported more cases of infection on those receiving the vaccines than on those which didn't receive the vaccine. And we started to worry about and try to understand why that was happening. So in summary, we have found out that all the individuals participating in the trial that were under 9 were majority seronegative individuals. So they have never been experienced any infection. And that's what happens for individuals between 2 to 5, 6 to 8, and then between 2 to 8. So I just combine both to get an average vaccine efficacy over time. So for very young ones, you have a stable positive vaccine efficacy that dropped really badly, and even with all confidence interval within the negative vaccine efficacy, and it went up again, but then after that, I didn't have information on this data. For those which were between 6 to 8, the vaccine efficacy was dropping, continuing dropping, with large part of the confidence interval into the negative vaccine efficacy. And to be fair, we just put those data together when we analyzed that the first 2 years we had a positive vaccine efficacy dropping towards a negative vaccine efficacy and was kept constant. And the hypothesis here is that because individuals are so young, they were not exposed to the infection yet, on contrary to those which were older 9 and have lived more time in these endemic regions, having been experienced more contact or exposition to the pathogen. So on the other hand, the older 9 individuals, 80% of the population was seropositive. And the vaccine efficacy was then estimated for this age group, or this immunological group, immune status group, showing that you have 2 years of stable positive vaccine efficacy, but still dropping when you are between 9 and 11, and dropping, but still higher when you are older. That we observed in the data. We did the same thing. We put both data together. We observed that the vaccine efficacy is not static. It changes over time. And of course, since the immunity of the population grows or decays, more people come into the population as a seronegative, it will be variable. But we were worried with that the thing was not the age, but was the immunological status of the individuals prior to vaccination. Okay, so we decided to have to evaluate the system with 2 different vaccine efficacies. And our assumption was that individuals of any age in the model, if they are seronegative, they have lower vaccine efficacy than if they are seropositive. Okay, so we use the year 3 as a vaccine efficacy average to simulate the effect or the impact of this vaccine in the population. Okay, So this is the two-strain model we just used, we just decided as by parsimony law to be extended. What have we done here? We took this model where we have seronegative being infected for the first time with strain 1 and strain 2, recovered from the primary infection and become susceptible again, and after becoming susceptible again, get a secondary infection with a different strain from the primary infection. That's our minimalistic two-strain model that I just presented to you. This vaccine was then recommended to individuals older than 9. Yeah. So I stratify my model by age, where I have individuals younger than 9, individuals between 9 to 45, where the vaccine can be used, and individuals older than 45, where the vaccine is also not recommended. So I introduce the vaccine in two possible ways. I can vaccinate those individuals being seronegative or being seropositive. Given the vaccine efficacy information I have, if I vaccinate seropositive individuals, I protect them, I have a positive vaccine efficacy, and I move these individuals from the class S to the R. So I avoid secondary infection, I avoid hospitalization. However, if I vaccinate seronegative individuals, I move those individuals into a class of sensitized individuals, vaccinated individuals. So I assume that the vaccine acts as a primary infection, and when those individuals acquire a natural primary infection, they do not pass through this phase here, but they move immediately to this phase here. So in this case, you get an increasing of hospitalizations when you vaccinate too many seropositive. The dynamics for the below 9 and over 45 are kept the same because they are living an endemic scenario, so they can go through the disease-related stages, but they are not vaccinated. Okay? Please let me know if something is not clear. We continue. What have we done afterwards? We use the data we have available, and knowing that we have 10 years of prediction horizon of our system, what we did was we start validating and parameterizing our model with this data set by matching periods of 5 years in order to get prediction of other 5 years. So this is two examples of model matching using the same parameter set. For example, here between 2002 and 2008, the data is in green and the model simulations in red. We have a good agreement, qualitative agreement. And another set of 5 years between 2011 and 2016, where we have the data in green and the model in red, also qualitative good agreement. That was the last data we had available. So we match these 5 years and we introduce the vaccination and we look at the next 5 years. Okay, that's the exercise we did. We matched the last 5 years of data we had. We introduced the vaccination as such. We covered 4% of all the population between 9 to 45 years old during a period of 5 years. And this was decided because when the vaccine was licensed, the producer have said, with this vaccine, if you vaccinate 20% of the population, you decrease the severe cases, you decrease the hospitalizations in 50%. So you wanted to check what would be the situation really. Again, remember that we have around 10 years of prediction horizon given the Lyapunov exponent calculation. So we match 5 years and we predict the next 5 years. Two ways to predict, to evaluate the implementation of the vaccine. We can vaccinate the population between 9 to 45 without screening, without separating them as seropositive or seronegative. And when we do that, given the vaccine efficacy we have calculated, we have modeled, we see that after 5 years, you have an increase, not a decrease. You have an increase of hospitalizations when you do not screen the population. And the suggestion was to look at vaccination only on those which have been already experienced an infection and vaccinate them. I don't know if you can see here, but the result would be here, this light blue-green, and the average over 5 years would be a decrease of 40%. So this figure here shows the vaccination without screening in black and the vaccination with screening in light blue. And while we do not screen, you have an increase of hospitalizations, but if you screen, you have a decrease of hospitalizations, okay? We did a sensitivity analysis of the vaccine efficacy used in one or another age class by assuming difference between seropositive and seronegative. And the result here was a completely counterintuitive result because When you have a vaccine, especially against to protect children, we expect that as younger as you vaccinate, more you protect against the number of infections in the population. And when we look at it, and let's fix in this one here, the vaccine efficacy estimated that we use to do this exercise here, we see that as younger as you vaccinate, more hospitalizations you have as older you vaccinated. And that's because in the older individuals are more exposed to the virus than younger individuals. So to be seronegative or seropositive is correlated with age, especially in endemic countries. In 2017, there was some information coming on the immune status, and that was kind of shooting their own foot. They released data on the vaccine efficacy for seropositive and seronegative. And what we have done was to compare first individuals at the same age having experienced infection or not, so having been seropositive or seronegative, and we plot here the vaccine efficacies, and we see that those distributions are not lying on top of each other. So seropositive and seronegatives at the same age have different profiles. However, when we look at seronegative only, when you look at seropositive, seronegative only, independent of the age, you see that both distributions are lying on top of each other. So the immunological status bring together the age classes rather than the age classes showing any kind of impact itself within the vaccine efficacy, although we know that's correlated, okay? So what we have shown here was that the individual serostatus would be the most important feature when we look at the vaccine efficacy for the Sanofi Pasteur vaccine. And you should rather focus the vaccine into those individuals which have been already infected than those which have never been infected. This is costly. We have a vaccine which only works with those who have already been infected, and you have to test them before vaccinating. So what would be the cost benefit for this vaccine? That was really a big issue, and we kept fighting with them on that. And here is the summary of the story. So in April 2016, this vaccine was recommended by the WHO, suggesting even though after observing that a high rate of hospitalizations in seronegative children were observed in comparison to those which have been already exposed to the virus or to the seropositive. End of 2017, vaccine was implemented in 2 large vaccination programs, one in the Philippines, even before the vaccine was licensed. Philippines has vaccinated more than 1 million children, and the south of Brazil, where dengue is not a problem, vaccinating more than 300,000 people there, most of them seronegative, without any pre-vaccination testing. So by the end of 2017, we managed to publish our results, and Sanofi then started to perform a new test on those participating in the trials. And they observed that, in fact, seronegative individuals were experiencing, were developing the severe disease in comparison to those seropositive. So they just suspended the vaccination program. And finally, after 2 years, the WHO released a new recommendation requiring a pre-testing of this vaccine. So although this vaccine is now licensed, they can only be used to those which shows a positive dengue infection before, prior to vaccination. And that's all to say that that was a bump that could have been avoided since 2 years ago when we started talking to them that there was a risk and you should look at the immune status and so on and so forth. For the dengue vaccine that's just finished this phase 3 trial, unfortunately, although we see the more balanced difference between seropositive and seronegative, we still see some negative vaccine efficacy coming out for a specific dengue virus. And that means that efficacy and safety conclusions for this vaccine before the vaccine is being licensed should be longer observed than it was done for the dengue vaccine. Good. So that's my last slide. We have done much more in dengue, and you can just give a look at the publications. They are really didactical, even though if you are not a modeler, it's easier to understand, modestly speaking. And the next lecture would be how our learning process on dengue can be used to understand the spread of COVID-19. How can be used to evaluate the impact of COVID-19. So this is only to give you a bit of flavor. This is the COVID-19 dynamics model by the Shadow City model that I have discussed with you yesterday. This is the cumulative number of hospitalizations, ICU admissions, and disease, and this is the number of incidences. Our model are really well describing the data, and we are going to discuss that on Thursday during the last lecture of my mini course. I thank you for your attention with a message here that we have a conference, yearly conference, that's already at 13th, the SABNS Dynamical Systems Applied to Biology and Natural Science conference that is being virtual again this year in February 2022. And if you are interested in knowing deeper techniques on models or mathematical models in epidemiology, we are going to organize a course at BCAM in spring. And for more information on our MTB group, please follow us on Facebook, especially Facebook. I'm not really a big fan of Twitter, but we are there as well. Thank you.
Okay. Thanks so much, Maíra. I have sent through the chat that if anybody wants to ask some questions, just write in the chat or turn your micro on. So any questions here in the audience?
Ya está. Hi.
Hi.
Just one question. So the dengue infection is a mosquito-borne infection, right?
Yeah.
And apart from the time-dependent infection rate, there's no other way in which that comes into the models. Am I right?
No,
So,
you can add the explicit vectorial dynamics. Let me see if I find here a slide to show you. I mean, you add 2 or 3 or 4 more equations into the system, but I would only advise you to do that if you have any question regarding the vectorial dynamics itself. First, because data on vectors are not reliable at all. We have very little data. And second,
okay,
because, yes.
Sorry. So yeah. My question was just out of ignorance if there is any course of action regarding the mosquito population, for example, whether it is monitoring or doing anything else to the mosquito population in order to contain the epidemic.
I said, if you want to look at the control of vectorial dynamics, you have to add the dynamics for the mosquitoes. In this model, without explicit equations for the vectors, you cannot do anything on that.
Okay, thank you.
Yeah. There is one exercise we have done by adding, so comparing the system with seasonal system and the two simple SI for the vector model. It doesn't matter, okay? In terms of dynamics, it doesn't matter at all. So I would, I tend to say to the entomologists that mosquito dynamics doesn't matter. That's terrible, but you know, overall it is that. If you have data and you have a question, you of course need to include these equations. But other than that, better to keep it simple and use the seasonal forcing just to mimic the abundance and the decrease of vectors rather than adding the equations itself. Too many parameters and very little data to estimate the parameters.
So no more questions here. Okay, good. Very, very interesting. And epidemiology, unfortunately, is a hot topic now. So, okay, so we will finish today's lecture and well, see you tomorrow, everybody.
All right. Bye-bye. See you tomorrow.
Bye-bye, Maíra. Thanks so much.
Thank you. Bye.
Bye.